Today we'll be covering a new topic in integration, which is integration by substitution. And this is basically just a new method for solving integration problems that you'll come across. So, integration by substitution, basically it's used in examples like this, where we've got something that we would normally look at using a product rule or a quotient rule. So here we've got a function, it's 12x squared times another function, which is the square root of 4x cubed plus 3. So normally if we were differentiating this, we would look at using the product rule. But unfortunately, there is no product rule for integration. So what we have to do is this new method, which is integration by substitution. And the idea behind this method is you take your variable, in this case it's x, because that's what we're integrating with respect to, and we find a new variable that we can define our integral using. And from there, we do the integral using our new variable. In this case, it's going to be u, and that new variable is equal to 4x cubed plus 3. So we want to get the whole integral in terms of u, and then we integrate it in terms of u, and then we sub it back in for our u to get it in terms of x. Now, that seems like a lot, and that may not make too much sense at the beginning, but I'm going to go through a couple of examples, and hopefully that'll make a bit more sense. So, what we want to do is we want to replace all our x's at this stage, and we want to get them in terms of u. So, if we have a look at this initial expression, then the 4x cubed plus 1 is really easy to change, because that's just going to be u. So that's a really easy thing to substitute. But we want to get rid of all our x's, which means we also want to get rid of the 12x squared, and we're also going to want to get rid of that dx. And let's just go over how to do that. So I'm going to show you the general techniques of doing these questions, and you should basically just copy the same sort of methodology with any sort of substitution question. So what we do is we start with our initial substitution. So we let u equal to 4x cubed plus 1. Now, what I want to do is I want to get something that will replace my dx. So I want to introduce dx into this, and then I want to rearrange and solve for it. Now, dx is, we can get that using differentiation. So if I differentiate this, both sides, with respect to x, then what I'm going to get is the derivative of u with respect to x is equal to, and if I'm differentiating this, I'm going to bring the 3 down the front and minus 1 from the power, so that's going to become 12x squared, and the plus 1 just disappears. So now I'm going to rearrange this for my dx so I can get rid of it from my question. And so this becomes du divided by 12x squared equals 2 dx. And what I've done here is I've times my dx up and I've divided by my 12x squared. So now I've got an expression for dx. And so what I'm going to do now is substitute u equals to 4x cubed plus 1 and substitute. Sorry, I've misspelled that. Substitute. And dx equals to du over 12x squared into 1. And I'm just going to call that equation 1. And so what this is going to give is the integral. And we haven't done anything to this 12x squared just yet, so we're just going to leave it in there. But I'm going to replace this 4x cubed plus 1 with u, because that's all it is, square root of u. And now I'm replacing my dx with du over 12x squared. And so this is going to be equal to, because I've got a 12x here, 12x squared here and a 12x squared here, both of these are going to cancel. And I'm left with a very nice expression just in terms of u, square root u du. So now we're integrating with respect to u. So it's really important that you sub in for that dx, otherwise you're not going to get a du. So even if everything else is in terms of u, you'll still be integrating with respect to x, which isn't what you want to be doing. You want to be integrating with respect to your new variable, which means you need a du in this case. So now I want to solve the integral of the square root of u du. And this is actually really easy. This is just a normal integral. So if we integrate this, another way of writing it is the integral of u to the power of a half du. And so it's just like normal integration. I'm going to add 1 to the power and divide by the new power. So this just becomes 2 over 3 u to the power of 3 over 2. So when I add 1 to a half, I get 3 over 2. And when I divide by 3 over 2, I get times by 2/3. But we're not quite done yet, because what we're going to do now is substitute back in for our u. So substitute, oops, misspelled that again, substitute. U is equal to 4x cubed plus 1, which implies that the integral of 12x squared, the square root of 4x cubed plus 1 dx is equal to, and the final answer is going to be equal to this when we substitute back in our 4x cubed plus 1. So we get 2 on 3, bracket 4x cubed plus 1 to the power of 3 on 2. Now, personally, I don't like we shouldn't be writing it this way with the 3 on 2 in the fraction, because in our initial question, it gave it to us in terms of surds. So I'm just going to convert this back into surd form. But this is just to show you that we are literally just replacing that u with what it should be based on our substitution initially. But I'm just going to put that in surd form, which gives us, since it's 3 on 2, all of this will be to the power of 3, and then it'll all have a square root over the top. But that is our answer, and that is in terms of x. And so we've been able to do that rather simply using substitution. And the main points of substitution are, we initially start with our substitution and get an expression for dx or dy, depending whatever your variable is here. And we get it in terms of the new variable. And then step 2, we are going to substitute in the new variable and our dx term, or our dy term again. And that'll give us an expression just in terms of u, which is really good. And then our third step is to solve that expression, solve the integral we get. And we have a bit of a fourth step in that we have to then substitute back in from the very beginning what we initially had. So we've got it in terms of the original variable, because that's the variable we care about here. So it's just those 4 basic steps. We solve for a dx, we substitute everything in, then we solve the new integral, and then we substitute back in to get it in terms of the old variable. So this was an indefinite integral example, so let's just go over a definite integral example and look at how the boundary conditions will change what we do with the integral. So in this one, we've got the integral from 0 to pi on 6 of cos to the 4x sine x dx. And again, in this example, how would you normally do it? If you were differentiating, you just do the product rule. It'd just be, you'd use cos x to the power of 4 and sine x, and then you just solve using the product rule and a little bit of the chain rule here, because you've got a to the power of 4 here. But you just do that, and then you'd solve it, and it'd be fine. Unfortunately, though, we don't have a product rule, so we will be using our new method, which is integration by substitution. Now, the steps for a definite integral example are very much the same as the previous one, just with few more steps with this, involving the boundary conditions. So, what's our substitution here? It is u is equal to cos of x. You're given that in the question, so that's the substitution we will be using. So, what was step 1 from before? Well, step 1 is we start with our initial substitution, and then we want to get a dx term out of this. So what are we going to do? We're going to differentiate this. So that implies that du dx is equal to negative sine x, and that's just the derivative of cos. That's nothing new. But then when we rearrange this, I'm going to multiply by dx and divide by negative sine of x. And so that's going to give du over minus sine x, which is equal to dx. And done. So that's now our derivative. But because this is a definite integral example, there's one thing I'm going to do before I substitute in, and I'm going to deal with the boundary conditions. Because this is a boundary condition of saying essentially that x is less than or equal to 0, but x is greater than or equal to 0, and it is also less than or equal to pi on 6. So when I'm substituting in for u, I'm not going to have those same boundary conditions because u doesn't have the same boundary conditions as x. So what I'm going to have to do is I'm going to have to now find the boundary conditions of u rather than x. And the way I'm going to do that is I'm going to take the cos of both sides, because that's exactly what u does. I'm going to take essentially my x values. So when x is equal to 0, u is equal to cos of 0. And what's cos of 0? Well, that's just going to be 1. And then when x is equal to pi on 6, I'm just going to then have u is equal to cos pi on 6. So that's just cos of 30 degrees, which you can get from your exact value triangles, which is just root 3 on 2. So nothing new there. But that tells us that our boundary conditions aren't 0 to pi on 6. It's actually 1 to root 3 on 2. Now, the more astute among you may know that root 3 on 2 is actually less than 1. And that's important because we actually have to leave the order the same. So when we substitute in, which is our next step, substitute, keep misspelling that, substitute in, what we're going to get is the integral from 1 to root 3 on 2. And now normally we have the larger integral, the larger number on top, because we're going from the lower condition to the higher condition. But with this substitution, it's really important that you make sure the order is the same. So since when we substitute in for our 0, that's on the bottom, we're going to leave the 1 on the bottom, and you don't want to put the higher one up top unless it was there already. Anyway, so substituting for the rest of it, we have our cos x to the 4. That's just going to be u to the 4 because u is cos x, so that's just u to the 4. And from here, we've now got our sine x. We didn't do anything to that, so we just leave our sine x. And then we have a dx. Now, our dx is equal to du over negative sine x. So we get du over negative sine x. And so from here, we just simplify. So this just becomes the integral from 1 to root 3 on 2, u to the 4. And the sine x's cancel, and we get negative sign out the front, and du. And so that's essentially our integral. And so now we just need to solve our integral. So now we need to solve. So that means that the integral of pi on 0 to pi on 6 of cos to the 4 sine x dx, this is just going to be equal to that integral we had from our substitution, 1 root 3 on 2, u to the 4 du. So now what we're just going to do is we're just going to solve this essentially, and there's no more to it than that. And so what we get is we get minus sign, and if we do this integral, we just add 1 to the power and divide by the new power, so we get u to the 5 on 5 on 5, and it's going from 1 to root 3 on 2, and so that's just going to give negative root 3 over 10, root 3 over 2 to the power of 5 over 5 minus 1 to the power of 5 over 5. And then you can just put that into your calculator, and then you're done. And so essentially what we've done in this method is we've done the same thing as what we were doing earlier, except now we had to deal with those boundary conditions, which is just a little bit different. And it just makes you have to pay attention to what those boundary conditions are, and you really, really have to make sure that you put them into the right order. Otherwise, you won't get the question right. Because when we come over here and do this integral, and we do the definite integral for this, then we're not going to get them in the right order, which means this negative sign is going to be on the opposite one, and that's going to give you the wrong answer every time, except in a very few cases, so you really have to pay attention to this. Or else you could do everything else perfectly correct. Just because you put them in the wrong order, you could get the answer wrong, which is going to cost you marks. So what were the main steps here, and how did it how did it differ than an indefinite integral? Well, we had our first step, which was our finding our dx, and that was the exact same as what we did earlier. And then in our second step, we had to find our boundary conditions and put them in the right order. But then our third step's the same in that we were just substituting in and solving. Well, substituting in and getting it ready for our fourth step, which is solving. And with this one, we just go through and we just solve the indefinite integral. And importantly, with these ones, because it's a definite integral, we don't ever have to substitute back in to get rid of our u's, because we're already going to do that with our new boundary conditions with our numbers. So we never have to actually substitute back in. We can just solve it using our u variable, because at that stage we're dealing with numbers. We're going to get the same numbers out no matter what we do. Anyway, I hope that this lesson was helpful and that you have a bit of a better understanding of integration by substitution. And I hope to see you guys in the next video.